In this problem, we're considering how water is flowing out of a tank. It's a conical water tank, so shaped like a cone, the vertex down at the bottom here like this. We're told a few pieces of information about the tank itself. Radius of the top is 2 meters. Overall, the height here is 4 meters. And we're given how quickly the tank is leaking out in terms of a rate per second. So we'll have to think about that in a moment. What we're interested in is how fast the height of the water in the tank is changing when we're down to a half full moment. Okay, so what we're always looking for first is an always true relationship. And to make it a little more specific, we are looking for the height of the water, or more particularly its rate of change. So that means we have to imagine that there's some depth of the water at a particular moment. We're going to call that height h. And what we also know is changing is the volume. So there would be a volume of water in this tank, and that would be a function of time as well. So what we want to do is relate the volume to the height, because then we can relate the rate of change of the volume to what we were asked for, which is the rate of change of height. So we want a relationship between h and v. All right. So how do we go about doing that? Well, we're going to need some pieces. Let's first off read what we know here. We put the dimensions on already, but we're also told that the water is leaking out at 0.5 liters per second. Well, that's a unit of volume per second, so that translates to a dV dt of 0.5 liters per second. And you have to be a bit careful here. Is the volume increasing or decreasing? Well, if the water's flowing out and V represents the volume actually in the tank, then V is decreasing, which means we definitely need a negative sign in front of this. And what we'd also expect as a result is that H will have a negative derivative. H should be decreasing, so when we start looking for dH dt, it should be negative. So that's what we want, dH dt, and if we do our calculations right, it should be negative. Okay. Well, how are we going to relate our depth of the water and V, our volume of water? Well, we have a nice cone here, in fact. There's a nice relationship between the volume of a cone, which is that V is going to be equal to 1/3 pi the base radius squared times the depth, or height. Now, one of these we know, we call the depth of the tank h. What we haven't put on here is the corresponding radius, let's call it r here. And it's going to change. It's going to get smaller and smaller as we empty the tank out. But we have a lovely similar triangle construction we can make now. If we look from the side, there's the master triangle, which is 2 by 4, radius of 2, height of 4. And there's its internal one, which is the triangle we can draw with it, where the water is. And it will have a height h and a radius r. So if we want to know what the r radius is, we can find it based on the height h, and it's going to be a 2:4 ratio. So 2:4 is equal to r to h. 2/4 is equal to r over h, or the radius that we're talking about is going to be 1/2. It's 2/4 is just 1/2. And then we bring the h up, we get an h there. So our volume is going to equal 1/3 pi the radius squared, 1/2 h all squared, times the depth, which is h. And we can tidy that up a bit. That'll be a half squared is a quarter, times a third is 1/12. Let's bring the pi front. And we have an h squared times h. We will end up with h cubed. And the nice thing about this statement here is that it is always true. Regardless of how empty or full the water tank is, the volume of water in the tank will be related back to the depth of the water through this relationship here. Now, what does that get us? It gets us a relationship that we can differentiate. So we're going to take d dt of both sides. So we're going to take the time derivative of our volume, and that's going to equal the time derivative of our pi over 12 h cubed. Left-hand side is fairly straightforward. We notice that v is a function of time, so when we differentiate it, we just get dv dt. The constants on the right, the pi over 12, stays out front, that's fine. And then the derivative of anything cubed is always 3 times the same thing squared. And then we take the derivative of the inside. Now the inside is h, the derivative is with time. Those are two different things. So we get a dh dt out of that. And we're pretty close to in business now, because we just take a step back. The question asked, how fast is the height of the water, dh dt, changing when the remaining water is at a height of 2 meters? So at h equals 2. Well, we can just plug that in now and find out. Taking one step back again, 0.5 liters per second is the other feature we're going to need. So we know dv dt is negative 0.5 liters per second. Now I have to be a bit careful about this because our heights are all in meters. So if we ask ourselves, how is 1 meter cubed, which is what we had up here, related to a liter? Well, liter is 1 or 10 centimeters cubed. So we can fit 10 along one side, and then we fit 10 along the other side, and we fit 10 along the other side. So 1,000 liters, 10 cubed, is equal to 1 meter cubed. So if we go the other way, a liter is 1 over 1,000 meter cubed. So these kind of unit conversions we do expect you to have in your back pocket to bring out as necessary. So let's translate that here. It's going to be 3 more zeros, and then we can call those meters cubed per second. A lot fewer meters cubed because meters cubed are bigger. All right, and h equals 2. So what we can do is plug both of these into our equation, and we get negative 0.0005 is going to equal, well, actually we get pi over 4 here from the 3/12. Let's simplify that there, 1/4. And even better, if h is 2, we're going to have a 2 squared dh dt. And when we calculate that out, we can bring, actually the 2 squared cancels with the 4 perfectly. So, hey. So in fact, we just get negative 0.0005 all over pi is our dh dt. And we can find a nice round number for that if we like, using our calculator, which is approximately negative 1.592 times 10 to the minus 4 meters per second. Or, if you'd like this, and that'd actually be 10 to the minus 3 is millimeters, so negative 0.1592 millimeters per second. Yeah, backing off 4 decimal places. Now that might seem like quite a small amount, but if you look at the rates, we're actually losing very, very little water. You know, think of a milk jug. We're losing a milk jug, half a milk jug per second. In terms of the scale of the object we're talking about here, it's 2 meters deep of water. It has a cross-section at the top here of 1 meter still. It takes a lot of water to bring that down, even a small amount. So the slow rate of height change is not as surprising as it might seem at first glance when we look at all the units involved.